Hi, so this is take two on the series, and it's take two because the video got corrupted, so all the voice is gone, and it's just a black screen, so I have to do this over again. And but on the positive side, we already have things pre-written, so it 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 should be quicker. So on this episode we'll cover a series. What is a series? What is a sequence? Also, partial sums. We'll figure that out. So yeah, let's begin. So a series is a list of terms, uh, or rather a sum of terms. So a sum, and these could be as exemplified here, 2 plus 3 plus 5 plus 10. There could be a formula, so a formula like this one, the general form, uh, that describes the progression of the series. Um, the order of the terms here, they don't matter, right? And that's because, well, being a sum, we know that 1 plus another number will be the same as the opposite. So if we swap places, right? So commutation. So the order doesn't matter, and that's another property of the series. And uh, it is, well, you can substitute the terms. So like here, we can substitute them with variables to take further conclusions. This here is the general form, aka the formula, where Sn is the symbol of the series, and k is the last number, or the last, sorry, k is the last iteration, d is the starting iteration, and n is the variable which will hold the value uh, that each iteration will be. And then we have a, which is a term or a number of terms. A just obfuscates any, let's say, a sorry, a could be equal to, let me grab my pen for this. So a could be equal to something like x squared plus 1 over 2, something like that. And then you multiply this by n, or then n is somewhere like along these lines, so x plus n divided by 2 or something, or I don't know, plus 1. Anyways, so yeah, that's the formula for the series. Then we have a sequence. And what is a sequence? Well, a sequence is much like a series, where you have a list or a sum of terms. In this case, you actually have an ordered list. So before, when the order did not matter, say we could replace, because it's in a sum, right, the order of both terms. In a list, it does matter. So this is an object, right? We call this an object. And this object is composed of elements. So this element, this element, this element. And each of them are in specific indexes. So this is index 1, this is index, so index 0, pardon, index 1, index 2, etc., index n. And this is important, right? If we go on and compare two sets or two lists or two objects, notations, right? Sorry, you can use any terminology you want for this. Um, they're different, right? Because even if we invert the order and something like 3 and then 5, they're different. So the first one, the second one, and the third one, so 0, 1, and 2, the index position of the elements will be in different locations. So so the value corresponding to each index will be in different locations. So if they don't correspond, then the objects cannot be equivalent, and thus the order matters. So and yeah, and so sequences are important because we correlate a lot of information regarding series with sequences, as we will see. So the general form, which is to say the formula of the series, is a bit not very much, but still uses the same terms as the series. It's similar to the series in a way that we have an A, right? So we have the term, and then we have n, which is the iteration. So k is the final iteration. D is the starting iteration, like we have in series. So D, the starting iteration. K is the last one. Then we have the term, and then n, and this and down here. So n. We're just specifying where n commences, so we're equaling it to d, and then specifying k, which is the last one. But what really matters is what's in here. So this is meta information about the operation we'll be conducting inside, and this is equal to any bounded set. So you define the lower limit and the upper limit with d and k, and you instantly have a set. Sorry, so a set. Okay, so and these you can define or use the notation to address them. A1, A2 until AN. So it's not zero indexed. Okay, so let's so that is sequence, and so we went over series and we went over a sequence. What a sequence is. So a series is a sum, right? Is a sum of so it's a progression in which you have a sum, and the terms are summed up, and the sequence is listing the let's say some terms and listing them in a bounded manner. And so, and then we arrive at the concept of infinite series. So let's see. Infinite series is you say the beginning, so the iteration at which the sum begins, and you don't give it an upper bound. So you say it starts here and it goes ad infinitum. And an infinite series, so yeah, and an infinite series has some properties which we are more focused on in this group of lectures, this study field. And we'll begin with partial sums. So partial sums is having an infinite series studying a finite set within this infinite range that begins in D, right? So n equals D, and then goes at n, etc., infinite, right? But instead of going to extreme lengths and using very advanced calculus to trying to figure out some or take some conclusions, we define, so we have the starting point and we define a temporary end. So let's say we have 1, 2, 3, 4 elements, right? And we declare this the temporary upper bound, and we have this predefined lower bound. So k temporarily changes from infinite to something that we specify. Uh, Another definition of partial sums could be one of, well, there are plenty actually, but the ones that we need are essentially that one, and the other case, which is when we have the infinite, and this one is a bit more specific. So when we have an infinite series, we can pick out, let's say, more specifically, we have a of n, and then we have, let's say, a1, a2, a3, right? And then we have a minus n, so sorry, a n minus 1 and a n, and we have some etceteras in the middle. So let's say that we have more elements. So we have the first one, the second one, the third one, and the problem here is, so what we're trying to use partial sums for is determining behaviors, right? So what does that mean? Well, so let's see, we can start observing patterns, right? So how this number changes to this number, and how that number changes to this number, and though we're not looking at the whole set, we ignore the middle part. We just study the beginning elements of the series and the partial sums, using the partial sums, and we look at the final terms of the series also to try to conclude something from it. So we'll see more about that. Okay. So let's see. So let's say that we have a series, and we want, so, and we provide the boundaries. The lower boundary is 10 and the upper boundary is infinite. And then we provide the term for a of n. So here we substituted by 2 to the n, so we got 2 power of n, and we get this. And we wanna see how this series behaves. But it's an infinite series, so we say, instead of trying some crazy stuff, because infinity is insane, we will just set an upper bound, and we will take a lower number and explore how these terms, right, in this scenario, so it has, so partial sums has two behaviors, and this is one of the behaviors. So the first behavior is we study how the how the progression works, how the behavior of this series occurs throughout a interval. And the other behavior of the partial sums is, or the other option you can take is to verify or do the exact same, but just for the initial 3 iterations, for example, or 5 if you want to be more cautious. So let's say normally we just take the initial 3 and the final 3. So we do something like a0, a1, and a2, and then the last 3 is a n minus 2. Then, so let me take these out of the way. So those were the first 3. Then the last 3 will be a of n minus 2, a of n minus 1, and then a of n. And these are the last terms, so, of the partial sum. The beginning terms, and just to reiterate, the beginning terms. So the beginning three is A0, A1, and A2. Okay, so given that, here's what we can do. So it's healthy to specify if it is for the interval. It's healthy to say that it is inclusive or exclusive. In the first case of using the partial sums, we should say that it is inclusive. So we know that we are studying in the range of 10 to 14. Let's say, for example, which is to say that n will assume the number 10 throughout n to 14. So, and how will it work? Well, so we studied the series using partial sums by first setting the terms in variable form, including the last one and the first one is by default included. We get 5 elements, right? So the element 0, 1, 2, 3, 4. So 4 iterations, and these so we substitute n by the effective number, which increments by 1 at each iteration until 14, which is the upper bound temporarily that we define for the study of the partial sums. Right, and then we get these results. So the first iteration we have 2 to the power of 10, and then we get 2, and we sum it because it's a sum, let's not forget. So we sum it to 2 to the power of 11, 2 to the power of 12, 2 to the power of 13 and 14, and then we can convert it to their respective results. But the general idea, right, of doing it like this is not to, in the end, sum all of the numbers. It is to just put them in various forms, how many you can think of or like, because the idea is to establish a pattern. Okay, so the idea of doing this is to take some conclusions, like could we perhaps, for example, just from the these numbers, this sum, could we deduce the series itself, for example? So reverse engineering the series. For example, this is one thing that partial sums can do. It can do more, but and the big reason we're gonna need it is because it's a hugely important tool for later figuring out which type of series. So establishing the pattern to figure out which type of series we can be looking at. So it could be a geometric series or a p-series or lots of series, and by understanding the pattern we have rule sets that we can follow for each of those scenarios, and those rule sets allow for easy solving of the series in terms of figuring out stuff like convergence and divergence and other things. So for example, as I was saying, we could reverse engineer using the partial sums. We could reverse engineer the series itself, but here's some nuances, right? If you pick out the first two numbers, you could arrive at the incorrect conclusion that we are just always multiplying the first. For example, we could arrive at the wrong conclusion that we're just multiplying 1024 times 2 to arrive at this number. And you could, if we only try to study A10 and A11, so if we only pick those out and didn't care about the rest, we could take a wrong conclusion from that. And the same is true if we take, not for this case in particular, but if we take, and this is the problem with the partial sums, is that you may inevitably take wrong conclusions. It's not a perfect method, right? Because in truth, we're not multiplying the term by the nth, let's say, by the successive iteration. We're not saying it's this number times 2 equals that number, and we're not certainly not saying that it'll be the same, like this is in the third position, it will be this times 3. No, that's not true. That's it's so the fewer the numbers that we select for our study in the partial sums, the more likely or more prone we are to making some sort of mistake. So the more numbers we include in, the better. And when we try and we include the last numbers, that removes some margin of error. And in some cases, here we get straight answers, but it could be that we have some variables in the middle, and instead of getting this, we could get some x's and some y's and stuff like that. And by selecting the first 3, and well, in this case it's only 5, but it should be 6. So let's say that we get 3 in the beginning and 3 in the end. We can see patterns like x's that are being crossed, like cut. So let's say that they cancel each other and stuff like that. So partial sums are very powerful. Okay, so reverse engineering this is basically we see that this number right here, so I1 and I0, so this first iteration, second iteration, I2, I3, I4. We know that this, so I1 is equal to I0 times 2, and we see from I2 that it is I0 times 2, okay, and we times 4, and we see here that it is the same, so I0 times 8, and we can see a pattern here from the multiplication, and we pick out the same one like this, times 1. We see that there is a 1, a 2, a 4, and an 8, and this pattern is easy to recognize, right? We look at the other one, we see that it is equal to the initial iteration times 16. Well, this certainly looks like something we've seen in the past, right? It's the power of 2, so it's 2 to the power of 0, so the first iteration, 0 indexed, the first number, or the first multiplier we'll get is 2 to the power of 0, then 2 to the power of 1, it's this multiplier, then 2 to the power of 2, this multiplier, then 2 to the power of 3 is this multiplier, and finally 2 to the power of 4 is this multiplier. And so we see here that there is a progression, right? And this progression is, so what changes along it? The power changes. So along these numbers, along these terms, we see that there is a fixed portion, which is the base in this case. So the base is constant, and the variable, so the thing that varies, is a power, the power. And so we can conclude that if we want to convert this into a series, it would be, well, in the field of infinite series, we simply put the infinite up there, so by default, and we don't necessarily need to specify the starting position because we're trying to figure out the series, not where not any bound in particular. So let's just put the sum, and figuring out the bounds would be another exercise, but we just want to know the term here, really. So we know that there will be a 2, and the 2 is never changing, and then the thing that changes, well, that is the n, and it changes by 1, signifying that. So it goes from every term, sorry, every iteration, this this element is incremented by 1, so that is a pretty good indicator that this will be this will be n. So reverse engineering, it's one example of the many applications of partial sums, and we'll certainly see many more applications in the following series. So thank you for watching, and if you have any doubts or anything to add, please do it in the comment section. If you want to see more, subscribe and like, and thank you for watching. See you next time.